Hello everybody and welcome to the Kreatryx YouTube channel. I welcome you all in a fresh session of analog electronics. And my dear friends, when I say we are going to learn analog electronics from the very basic, I mean it. We will be learning from the very basic level to the very advanced level along with a lots and lots of questions. So before we do that, let me first introduce myself for my friend who is meeting me for the first time. My dear friends, my name is Ankit Goyal. I got AIR1 twice in GATE in 2014 and 2018. I was awarded the President of India Gold Medal in the year 2013 when I graduated from IIT Indore. Till date, I have trained more than 1 lakh students in the online and the offline classes and presently working as a director at Unacademy for GATE department. But my dear friends, the reason behind this series is because of the huge demand of analog electronics and the belief that whenever you ask for anything, we are there to deliver. Yes, my dear friends, we are here for you. We are here delivering for you. And when we say it, we will support you to the very fullest level. And this series will help you crack GATE with the top rank. It will enable ECE student to get 12 out of 12 and 5 out of 5 for electrical students. So my dear friends, if you want to learn with us live, then you can join Unacademy using the code Ankit ESE to get an immediate 10% discount. And not only, my dear friend, 10% discount, it also brings you under my guidance so that I can help you do something that I have done. I can at least take you near to this goal. Okay. So if you also dream the same thing, then join me in this journey on Unacademy subscription using the code Ankit ESE. Now, my dear friend, if you like the content that I deliver, you can watch more of my free videos on this URL, tinyurl.com/AnkitESE. Here you will find all my videos arranged subject-wise, chapter-wise, and you will find great content for free. And you are definitely going to love it. You are definitely going to enjoy. It not only includes conceptual videos, but it also includes problem-solving sessions. So just visit this once and you will fall in love with this URL. Don't forget it. It is a lifeline for you. And if you love the content that we are delivering on YouTube, we have created the first ever video book for you guys, where you will find all the videos along with all the notes that we provide arranged subject wise, chapter wise. So now, my dear friends, your dreams are no longer dreams. They are becoming a reality because you are getting a top quality course, well arranged, well structured, and that too for free. So what can be better than that? What can be better than that? Nothing, my dear friends. So we have empowered the dreams of those who earlier used to think that only the person with a huge amount of money can crack GATE with a top rank. No, my dear friends, that is not the case. Even you can do. Even you can do it. But yes, just you need to believe in yourself and visit this link. But remember, this is a case sensitive link, so write this in uppercase. Other than that, if you join plus subscription, you get all the top educators like me teaching you live in daily lectures, along with providing you daily practice paper, weekly quiz, test series, previous year question, practice question, crash course, rank improvement batch, and most importantly, clearing your each and every doubt. So if you join plus subscription, it is an entire world inside it. So you don't have to look outside. Once you enter plus, every need of yours will be taken care of, and we will make your journey as smooth as possible towards that destination of getting under 100, under 10 rank. Believe me, my friend, you leave that strategy part to us. You leave the content part to us. You just work hard and we will make sure that you obtain the top rank in GATE and ESE. And Iconic is a big brother of Plus. Yes, this is a little brother. So Iconic gives you everything that a Plus subscription gives, along with much more. The major part of Iconic is this personal coach, a person dedicated to you on a daily basis to get you the top rank, guiding you, getting your schedule design, making your strategy. Everything that you need to get the top rank is being done by this personal coach. He'll also create a study planner for you, which you can follow blindly and reach your destination with utmost ease. They will be analyzing your test result and tell you where you are lacking, how you can improve. So that way, my dear friend, everybody else will get a standard analysis, but you will get an analysis just tailor-made for you. Along with it, we have included study material additionally, theory and question bank, and soon we'll be introducing interview guidance into this. So this will become a complete package for a student who wants to take that journey from being an average student to sitting into a PSU or a MTech seat. So for them, this journey will be just like driving a Lamborghini to work. So that sort of a experience, that sort of a royal experience we are going to give you. So let's move on to the lecture, and if you want to join Unacademy, just make sure you use the code Ankit ESE to get my guidance as well as to get 10% over and above whatever Unacademy offers you. So now let's move on to the lecture, dear friends, and let's see what we have in store for you.
Hi guys, in the previous video I showed you some of the problems based on non-linear application of OPAMP. In this video we'll take a look at some more problems based on non-linear application, so that your concept is cleared and you understand how to tackle different kind of problems that can be asked in GATE. So the first question on your screen is the output voltage of a regulated power supply. Now this power supply we have studied twice. Once I discussed about this in diode circuits. There when we were talking about voltage regulator, a voltage regulator was basically being used to generate a power supply. Then we studied voltage regulator again in BJT, and now we are studying voltage regulator in case of your OPAMP. Okay. So first of all, this diode must be a Zener diode, because in power supply we always use Zener diode. It is giving us the Zener voltage as 3 volt. Now see, what will happen is this BJT in a power supply is always biased in active region. If it is biased in active region, then we basically have negative feedback. If you have complete path of negative feedback, then basically you can apply the concept of virtual ground. Okay. If I can apply the concept of virtual ground, what I will say is the positive terminal voltage should be equal to negative voltage. It should be 3 volt. Okay. So now I know this voltage is 3 volt. We know that OPAMP does not consume any current. If OPAMP does not consume any current, then this current I will be same as this current I. So if you apply KVL, you can see that both 40 kilo ohm and 20 kilo ohm are carrying the same current. So we can say 40 kilo ohm and 20 kilo ohm are in series. Okay. If they both are in series, how we can find V0? V0 is simply I into 40 plus 20. What about I? I is simply 3 volt by 20. So 3 by 20 into 60, that is 9 volt. So the output voltage will be 9 volt. So this question is completely based on logic. Though the circuit at first seems very complicated, it seems very complex, but when you find out the correct answer, the question method is very simple. So don't get afraid whenever you see problems based on voltage regulator. Just use your brain and try and apply the concept of virtual ground. Next problem. A regulated power supply shown in the figure has unregulated input of 15 volt. Okay. Generates a regulated output V out. Using the component value shown in the figure, we need to find power dissipation across Q1. Again we will say that Q1 is biased in active region. In linear power supply or active power supply, the active device is always biased in the linear region or the active region. Okay. In that case, see what will happen is that this feedback path is getting completed. So negative feedback is present. So we can apply the concept of virtual ground. If you apply the concept of virtual ground, what you can say, positive terminal voltage equal to negative, it is equal to 6 volt. See, this is a Zener diode with a voltage of 6 volt. So this terminal voltage will also be 6. Now you can find this current I. I will be 6 by 24K, that is 0.25 milliampere. This current will also be I because the current input to OPAMP is 0. So you can find out the output voltage V out. V out is simply I into 12 plus 24. Since 12 and 24 both are carrying the current I, they are in series. 0.25 into 36, that is 9 volt. So we know the value of V out. But what we want is the power dissipation across Q1. Now for power dissipation we need two things. One is the collector to emitter voltage and other is the collector current. So power dissipation in transistor is VCE into IC. That is the power dissipation. For VCE, if you see that the collector voltage is 15 volt and emitter voltage is V out. So 15 minus V out. V out is 9. So this will come out to be 6 volt. What I need now is the collector current. So see, if this current is I load, what is the emitter current? Emitter current consists of two components, I load plus I. That is how much? I is 0.25 milliampere. What is I? L. IL is V out by 10. That is 0.25 milliampere plus 0.9 ampere. So it is approximately 0.9 ampere. Okay. In front of ampere you can ignore milliampere. Now if beta of transistor is assumed to be high, you can say that collector current is approximately emitter current, which is actually equal to how much? 0.9 ampere. So what about power dissipation in transistor? VC is 6, collector current is 0.9, 5.4 watt. See the next part of the same problem. If unregulated voltage increases by 20%, find power dissipation across Q1. So input voltage becomes 20% higher. So increment of 20% in 15 volt. So that is 18 volt. Then what about VCE? It is the input voltage minus output voltage. 18 minus 9, that is 9 volt. So what will be power dissipation in the transistor? VCE into IC, 9 into 0.9, that is 8.1 watt. Now I haven't changed IC. Why? Because V out is the regulated output. V out will remain same. As long as V out is same, this I and IL will also be same. So what I am saying is V out does not depend on V in. So V out is constant, hence IC is also constant. But it is asking percentage increase in power dissipation. Now the power dissipation is 8.1, earlier it was 5.4. So that will be the percentage increase, new minus old upon old, that is 50%. Okay. So the percentage increase in power dissipation is 50%. So what will be the answer? 5.4 and increases by 50%. Next problem. In OPAMP circuit shown, assume that the diode current follows the equation Is e to the power V by Vt. Now Vi is 2 volt, V0 is V01, Vi is 4 volt, V0 is V02. We need to find relationship between V01 and V02. Which is this amplifier? This amplifier is your which one? It is your log amplifier. So if I assume diode is on, in that case your negative feedback path is completed. Okay. If the negative feedback path is completed, what I can say is we can make use of virtual ground. That means this voltage will also be 0. So what about I? I is Vi by 2 kilo ohm. This current I will go into the diode. So Vi by 2 kilo ohm is actually equal to Is e to the power V by Vt. Now V is the diode voltage. If you apply KVL, you can say that V0 is 0 minus V, or you can say V is minus V0. So Vi equal to 2 kilo ohm into Is e to the power minus V0 by Vt. Okay. Now, if Vi is 2 volt, V0 is V01. And if Vi is 4 volt, V0 is V02. Now take the ratio of the second equation and the first equation. 4 upon 2 will become 2. 2 kilo ohm and Is will get cancelled. E to the power minus V02 by Vt by e to the power minus V01 by Vt. So 2 equal to e to the power, if you take it in the numerator, so V01 minus V02 is Vt ln 2. Okay, that will be Vt ln 2. Now the answer from this options will be D. Okay, so this is nothing but a log amplifier. Even if you don't remember the correct relation, no need to memorize. You can always solve it using the concept of virtual ground. Next problem. Consider the following circuit using an ideal op-amp. The IV characteristics is described, where thermal voltage is 25 millivolt, I0 is 1 microampere. V is the voltage taken across the diode for forward biasing, that means it is V. For input Vi equal to minus 1, we need to find V0. See, it is an inverting amplifier, right? Because the input is connected at the negative terminal. It is an inverting amplifier. In that case, V0 is proportional to minus Vi. So if Vi is less than 0, V0 is greater than 0. Vi is minus 1 volt, so V0 will be positive. If V0 is positive, this diode will get forward biased. If diode gets forward bias, your negative feedback path gets completed. So what I can do? I can apply the concept of virtual ground. In that case, this voltage will be 0 volt. So what is this current I? I will be 0 minus 1 by 100k. That is 0.01 milliampere. Okay. Or you can say 10 microampere. Since op-amp does not carry any current, this current I will be like this. That means the current through the diode is 10 microampere. So I can calculate diode voltage using this relation. This relation that is given. E to the power V by Vt is 25 millivolt minus 1. That means V is 25 millivolt into log of 11. Okay. So 25 multiplied by ln 11. How much will it come out to be? 59.947 millivolt. Now what about V0? If you apply KVL, you will say V0 is I into 4K plus V. I is 10 microampere into 4 kilo ohm plus 59.947. Kilo micro into kilo will be milli, 40 plus 59. So 99.94 millivolt. Okay, or you can say approximately 100 millivolt, which will be 0.1 volt. So the answer would be B. Okay. So what I have done is I have checked whether diode is on or off, and once it is on, I can apply the concept of virtual ground. Next problem. We need to find the transfer characteristic for the precision rectifier circuit. Precision rectifier, because when we use diode alongside OPAMP, their cut-in voltage is almost zero. If their cut-in voltage is zero, then they behave as ideal diode, and that is called as a precision diode. So the rectifier implemented using precision diode will work as a precision rectifier. Okay. So now, if you see here, there are two inputs, Vi and 20 volt. So it is difficult to deal with two inputs. What I'll do, I will find out the Thevenin equivalent of the two inputs, Vi 20 volt, 4R and R. This terminal I want to find out VTH and RTH. So what I'll do is, I'll assume a current like this, I. This current I will be Vi minus 20 by 5R. So what about VTH? It is Vi minus IR. So Vi minus 20 by 5. That is 4 Vi plus 20 by 5. That is VTH. What about RTH? For RTH, you will short circuit these two terminals. 4R and R will come in parallel. So RTH will be 4R by 5. Now let us draw the Thevenin equivalent. The input is now VTH. The resistance is RTH. It is connected to inverting terminal of OPAMP, and non-inverting terminal is grounded. Okay. Now this resistance is R. Okay. Now see one thing, how do we analyze such circuits? We analyze such circuits by using open circuit test. But now since we are very familiar with these circuits, I'll try and do something directly. First let me write down the value of VTH and RTH. Okay. Now see, the input is connected at the negative terminal. If it is connected at negative terminal, it will work as inverting amplifier. So what I'll say, if VTH is positive, then VA will be negative. Now it is connected to cathode of D2 and anode of D1. If cathode is negative, then diode is forward bias. But if anode is negative, the diode is reverse bias. Similarly, we will say VTH is less than 0, it is inverting. Output will have opposite polarity, VA will be positive. So the anode of D1 is positive, so D1 is forward and D2 is reverse. So D1 is forward bias and D2 is reverse bias. Now let us take the first case when D2 is forward bias. If D2 is forward bias, what will happen? We will replace D2 by V gamma because it is saying practical diode, and this will be open. If it is V gamma, I can apply virtual ground. This is 0 volt. and VA is minus V gamma. Okay. So now what will be the value of V naught? V naught will be 0. Why? 0 minus 0 ampere into R. So V naught will be 0. So in this case, when VTH is positive, when D2 is forward, V naught is 0. Okay. In the second case, D1 is forward and D2 is reverse. If D1 is forward and D2 is reverse, I will replace it by open circuit and this will be V gamma. Now this feedback path is completed. If this feedback path is completed, what is the current here? VTH by RTH. So the current in the resistance R will not be 0 ampere. It will be VTH over RTH. So how you will write V naught? V naught is 0 minus current is VTH by RTH into R. So VTH is 4 VI plus 20 by 5 divided by 4R by 5 into R. So R gets cancelled, 5 gets cancelled. So it is minus VI minus 5. Okay. Now VTH greater than 0 means 4 VI plus 20 is greater than 0, or you can say VI greater than minus 5. In that case, V naught is 0. VTH less than 0 means 4 VI plus 20 is less than 0. VI is less than minus 5. In that case, V naught is minus VI minus 5. Now let us draw this transfer characteristics. V naught versus VI. Now the threshold point is minus 5 volt. Okay. When VI is greater than minus 5, V naught is 0. So this line we will show for 0 volt. When VI is less than minus 5, it is minus VI minus 5. So at VI equal to minus 5, here V naught will come out to be 0. So it will be a straight line like this. Let me redraw this. It will be a straight line like this. Okay. The slope of this line will be minus 1. So that is the transfer characteristic of the circuit shown in the figure. It is nothing but a half wave rectifier, but it is not rectifying with respect to 0 volt. It is rectifying with respect to minus 5 volt. Next problem. In the circuit shown, what is the output voltage if the silicon transistor Q and ideal op-amp is used? Now why it is saying silicon transistor? Because in silicon transistor VBE is 0.7 volt. Now see, let us see this. Input is connected to negative terminal. It is the case of inverting amplifier. If it is the case of inverting amplifier, so when input voltage is greater than 0, the output is less than 0. V out. Here we have 0 volt. This voltage is less than 0. So this junction will be forward bias. Base ammeter junction is forward bias. Okay. In that case, what we will say is that VBE equal to 0.7. That means base voltage is 0, ammeter voltage is V out. It is equal to 0.7. So V out is minus 0.7 volt. Okay. So the answer would be B. We don't need to know whether transistor is in active region or saturation region, but we know base ammeter junction is forward bias. So there are two possibilities, either the active region or the saturation. In both the cases, VBE will remain as 0.7 volt. Okay. Next problem. In the voltage regulator circuit, again this question is based on voltage regulator. No need to be afraid. The solution will be very simple. The OPAMP is ideal. BJT has VBE equal to 0.7, beta equal to 100, Zener voltage 4.7. The regulated output is 9. We need to find the value of R. See, first of all, this transistor Q. In a voltage regulator, the device is always biased in active region, right? Now this V0 is 9 and this current is 0 ampere. Okay. So that means the current in 1 kilo ohm and R resistance will be same. Or you can say both these resistances are connected in series. If both are in series, what is the voltage of the negative terminal? V minus by voltage division 9 into R by R plus 1. Here I am assuming that resistance R is in kilo ohm. Now based on Zener voltage, what you can see that positive terminal voltage is 4.7 volt. And by virtual ground, positive terminal voltage is same as negative. 4.7 equal to 9R over R plus 1. 4.7R plus 4.7 equal to 9R. Or you can say 4.3R equal to 4.7. So R is 47 by 43, 1.09 kilo ohm. Okay, that will be the value of R. Next problem, again based on voltage regulator. For the voltage regulator circuit, the input voltage is 20 volt plus minus 20%. Regulated output voltage is 10 volt. If RL draws 200 milliampere, we need to find maximum power dissipation. Now see, positive terminal voltage is given as 4. We will apply virtual ground. This voltage will also be 4. So this voltage is 4. What is this current I then? I is 4 by 10 kilo ohm, or you can say 0.4 milliampere. This is the same current that flows in R1. Okay. 0.4 milliampere. What is the current here? The load is requiring 200 milliampere. Okay. That means the total current here, ammeter current, is I plus 200 milliampere, that is 200.4 milliampere, and I'll approximate it as 200 milliampere. Now V out is given as 10 volt and V in is 20 plus minus 20%. So what about collector to ammeter voltage across transistor? It is V in minus V out, that is 20 plus minus 20% minus 10. That means how much? It will lie in the range of either, if you take 20 plus 20%, that is 24, 14 volt, or 20 minus 20% is 16, 6 volt. But we need maximum power dissipation in transistor. What is power dissipation? VCE into IC. If you assume that beta is high, IC is approximately IE, that is 200 milliampere. So if you want maximum power dissipation, you need to take maximum value of VC. Maximum value is 14 into 200 milliampere, that is 2.8 watt. That is the maximum power dissipation that can happen in the transistor Q1. Next problem. Consider the constant current source shown in the figure below. Let beta represents the current gain of the transistor. We need to find the load current. Now see, this is a Zener diode whose voltage is V reference. The voltage of this terminal is VCC. So what is the voltage of this terminal? By KVL, VCC minus Vref. Now due to this negative feedback, what I can say, negative terminal voltage is same as positive terminal voltage, which is VCC minus Vref. Okay. Now this negative terminal voltage is directly connected to this point. So can I find the current I? I will be VCC, this upper voltage is VCC, minus V minus over R. V minus is VCC minus V reference. So it is V reference by R. Now we know that there is no current at the input terminal of OPAMP. So this current I will become ammeter current. But what we need? Load current. Load current is basically collector current IC. IC, so it will be downwards. IC is beta over 1 plus beta IE, or beta over 1 plus beta V reference by R. So it will be B. Okay. That will be the load current I naught, or you can say collector current IC. Next problem. The following signal Vi has a peak voltage 8 volt. It is applied at the non-inverting terminal of an ideal OPAMP. Transistor has VB equal to 0.7, beta equal to 100, LED voltage 1.5, VCC 10 and minus VCC minus 10. Okay. Now see, there is no feedback in this circuit. If there is no feedback, it is working in open loop configuration. In open loop configuration, it works as a comparator. Now, there is no input current to OPAMP, so 8 kilo ohm and 2 kilo ohm are in series. If they are in series, you can apply voltage division. 10 into 2 by 2 plus 8, that is 2 volt. Now see how this circuit will work. If positive terminal voltage Vi is greater than 2 volt, the output voltage Va is plus Vsat or VCC, which is 10 volt. If this is 10 volt, the BJT will turn on. If BJT is on, current will flow through the BJT and LED will glow. Now when V positive equal to Vi is less than 2, then negative terminal voltage is higher, Va is minus VCC or minus 10 volt. If it is minus 10, the current will flow opposite, but in BJT or NPN transistor, current must enter the base. So I'll say BJT is off, or you can say if base emitter junction is reverse bias, the BJT will be in cutoff mode. So this current will be 0 ampere and LED will be off. So you can say whenever input voltage is greater than 2 volt, LED will glow. So let us see how many times input voltage crosses 2 volt. It goes above 2 volt. Okay. So here it will glow. In this region it will remain on till Vi is greater than 2. Now once it becomes less than 2, it will become off. Okay. Then when it is greater than 2 again, it will again become on. When it is again less than 2, it will become off. Again greater than 2, it will be on. Again less than 2, it will remain off. Okay. Now see, First time it is glowing at this point, then second, then third. So it will glow how many times? It will glow 3 times. Glowing 3 times means you have to count how many times the LED goes from off state to on state. That is, it was off, how many times it becomes on? So it becomes on 3 times. Next problem. A PIN photodiode of responsivity 0.8 ampere per watt. This responsivity is studied in EDC. We don't need to worry. We'll only consider the units, ampere per watt. Is connected to inverting terminal of ideal op-amp, VCC 15 minus VCC minus 15, RL 10 kilo ohm. Now we are incidenting 10 microwatt power. We need to find the photo current through the load. Now see the unit of responsivity. It is nothing but current by power. That is, how much power are you incidenting and how much current is flowing. That ratio is called as responsivity. So now if I want to find the current through this photodiode, this I, it is responsivity into 10 microwatt. So this current is 8 microampere. Okay. Once I know this, I know the current input is 0, and due to negative feedback, what I can do? I can apply the concept of virtual ground. So the negative terminal voltage is same as positive terminal voltage, that is 0 volt. This I current will come here. So what you will say? V0 minus 0 by 1 mega ohm is I, 8 microampere. So V0 will be 8 volt. Once we know the value of V0 is 8 volt, I can find out the value of load current, IL. 8 volt by 10 kilo ohm, that is 0.8 milliampere. Okay. Or you can say 800 microampere. It is asking in microampere, so the answer will be 800. Okay. So what I have done is I have just used the units of responsivity and figured out the current in the photodiode, and then I have used basic concept of your op-amp, that is virtual ground. Moving to the next problem, it says in the circuit shown below, op-amp is ideal. Zener voltage of the diode is 2.5. At the input we are applying step voltage. At t equal to 0, voltage across the capacitors is 0. We need to find the time V0, time at which V0 crosses minus 10. See one thing. Initially this capacitor has 0 volt. This also has 0 volt. What is the Zener voltage? 2.5. That means initially Zener diode is not in breakdown region, because for breakdown the voltage across Zener diode must be 2.5. It is 0 right now. If Zener diode is not in breakdown region, Zener diode is only reverse bias, it will work as open circuit. If this works as open circuit, 1 microfarad and 1 microfarad are in series. Now due to this capacitors, we are completing the path of negative feedback. If there is negative feedback, we can apply the concept of virtual ground. That means we can say that negative terminal voltage is same as positive terminal voltage, which is 0. So can you find out this current I then? Vin minus 0 by 1 kilo ohm. What is Vin? After t equal to 0, it is 1 volt. So it will come out to be 1 milliampere. Now see what will happen. Initially my Zener diode is off. these are the two capacitors. This is V out. Suppose this is VC1, this is VC2. If I apply KVL, this is 0 volt. V out is 0 minus VC1 minus VC2. That is minus VC1 plus VC2. And we also know the current here. The current is I, which is I is 1 milliampere. If this current is entering the positive plate of capacitor, it will charge both the capacitors. And we know C dVc by dt is current I. Since both the capacitors are in series, what I can do? C equivalent is C1 C2 by C1 plus C2. That is 0.5 microfarad. So 0.5 into dVc, Vc by dt equal to current I, 1 milliampere. So from here you can say Vc is how much? It is 0.5 microfarad, 2000 T. But that is the combined voltage of Vc1 and Vc2. Since both are identical and both are in series, both voltages will be equal and they will be equal to 1000 T. Okay. So both will be equal to 1000 T. Now what will happen? We have a Zener diode here and it requires 2.5 volt to go into the breakdown region. If it requires 2.5 volt to go into the breakdown region, as soon as Vc2 becomes 2.5 volt, Zener diode will turn on. So when it becomes 2.5, it becomes 2.5 at 2.5 millisecond. So what happens after 2.5 millisecond? That Zener diode goes into the breakdown region. When a Zener diode is in the breakdown region, what you can do? You can replace it with a battery. That means now the voltage of capacitor C2 is fixed. What is the voltage? 2.5. This is 0 volt by virtual ground. So how you will write V out? It is 0 minus Vc1 minus 2.5. We need to know the time at which V out is minus 10. That means Vc1 should be 7.5 volt. Now we know at t equal to 2.5 millisecond, both Vc1 and Vc2 were equal to 2.5 volt. But we need to know the time when Vc1 is 7.5. The current I is going like this. Okay. The current I is going like this. So what I'll say, dVc1 by dt into C1 equal to current I. C1 is 1 microfarad. dVc1 by dt, current I was 1 milliampere. So that means dVc1 is 1000 dt. When you integrate, we know at 2.5 millisecond, it is 2.5. We need to know the time when it is 7.5. If you integrate the left hand side, 7.5 minus 2.5 is 1000 t minus 2.5 millisecond. So t will come out to be 7.5 millisecond. So at 7.5 millisecond, the output voltage V out will become 10 volt, or it will cross minus 10 volt. Is it fine? So initially, since there was not sufficient voltage across Zener diode, it was only reverse bias. But as soon as the reverse biasing voltage went beyond 2.5, it becomes breakdown, and then we can replace Zener diode by a battery. Okay, so that is the complete analysis of this problem, and I hope now you are able to understand how to solve the problems based on non-linear application. We have used diode, BJT, Zener diode, all with OPAMP, and I hope you are comfortable with such kind of question. They are very important from gate point of view. Okay, so in the next video I'll talk about the next topic, that is the filters using OPAMP, and this is all from this video. Thank you.
For 12 months the pricing is 3250, but if you apply the code Ankit ESE, it becomes 27225. For 18 months it will be 34650, and for 24 months 39600. Believe me my dear friend, this is the most affordable pricing, and the longer duration subscriptions are more cost effective as compared to shorter duration. Like here it will cost you 1650 per month. Okay, this will be 2000 per month approx. This will be around 2250 per month. Then if you go for Iconic for 12 months, it is 5250. With code Ankit ESE it becomes 45225, and 2-year subscription becomes 66600. So the choice is yours, but take a longer duration subscription for more cost effective solution, and to give GATE and ESE at least 2 times, so that if you once crack GATE, in the next attempt you can even get ESE. And other than that my friends, you can download the Unacademy learning app right now, because there we provide live classes for free, test series and live quizzes for free. And once you download it, make sure that you follow this profile. This is my profile, so that whenever I come live you will get the notification. And this is the Telegram channel for our team. Here you will find all the lecture links, all the lecture files, and all the links for the special classes. Other than that my friend, my personal Telegram channel also you can join, t.me/gateair1. Here you can get in touch with me and we can take this journey together. Okay. Other than that, we have other YouTube channels like Mechanical, Civil and Telugu, JE channel, Computer Science, Gate Question and Electrical Junction, Pathshala and GS Terminal. Electrical Junction contains short videos of great concepts. Pathshala provides you animated content. JE preparation can be done through these 2 channels, Unacademy SSC JE and GS Terminal. And you can refer the other channels to the other friends in respective branches, so that they can also be benefited. At last, I would like to say, please share, like and subscribe to this channel. Subscribe to this channel, and not only subscribe, press the bell icon so that you get notified whenever a new video comes. And share these videos among all your college group, among all your friends, so that we can create the first ever revolution of free education in field of GATE and ESE. Thank you to everybody for dedicating time to watching this video. Please move on to the next one as well, and take the benefit of all the free content that we are providing. And in case you have completed the series, do make sure you watch the other subjects available on this channel. Thank you.